Alright, so now let's talk about graphs of functions. And I want to begin first by talking about whether or not a given graph is a function. In the other examples that we did when we were trying to determine whether a given correspondence was a function, we were given either a diagram representation for a function, or we were given the function as a set, and we got to see that it was a function if indeed one input gave us one output. Now we can do that approach with functions as well, but there's an easier way to determine whether a graph is a function, and that is through the use of the vertical line test. So this is the vertical line test. If no vertical line can be drawn so that it intersects a graph more than once, then the graph is a function. So in other words, if you draw a vertical line and the vertical line only crosses the graph once, then it is a function. So let's take a look at this example here. We want to determine whether the following graphs are representing functions. And the first graph, it seems to be a circle. Is this one here a function? Well, if we draw a vertical line, we get to see that the vertical line is crossing the circle at two different locations, here and here. So it's not a function. Now, why does the vertical line test work? Well, it's because it is going back to the definition for a function. Notice that if I choose this particular x value, I'll call this one here x1, well, that x value has one output here, but it also has another output here. So a vertical line has multiple outputs for the same input. That's why if the graph is crossing more than once, then you're basically saying that, hey, the input has more than one output, so it's not a function. Now for the second graph, if I draw a vertical line here, well, okay, it's only crossing once, and it doesn't matter where I draw the vertical line, it's only crossing once, so it is a function. Okay, so we get to see that this next example, it passes the vertical line test, it's only crossing once, so it is a function. And this last one here, it fails the vertical line test. One input has two outputs, so it's not a function. Okay, so now let's take a look here at another exercise where we're trying to find out the zeros and the y-intercepts for a function. Now, what we refer to as the zero of a function, it's basically telling you, hey, for what inputs are the output 0? In other words, you can sort of think about the zero as being the x-intercepts, because they're the same thing. Whenever you see zeros, x-intercepts, and roots, they're all referring to the same thing. Now, let's take a look at this function. So the function is f of x equals to negative 4x plus 2, and we want to find out all the zeros for the function. So in other words, the x-intercepts or the x values that make the y value equal to 0. So let's see. We have f of x equals to negative 4x plus 2, and we want to see where this is equal to 0. So there we go. Here's the equation that we're trying to solve. Negative 4x plus 2 is equals to 0. So we take away 2 from both sides, then divide by a negative 4. And we get to see here that x is equals to 1/2. So there we go. These are the zeros for this function. This is the x-intercept. Now for part B, it's asking us, okay, so what is the y-intercept? So for the y-intercept, all that we need to do here is set the x equals to 0 to find the y-intercept. Okay, so in other words, what we're solving here is f, when the input is 0, what do we get? Well, we'll get a negative 4 times 0 plus 2, so we get a 2. So there we go. The y-intercept is x was 0 and y was 2. In fact, let me put them in color. So the inputs was 0 and the output was 2. Okay. All right. Now for part C, it's asking us to make a sketch of the graph. And the nice thing about graphing the intercepts, specifically for a linear function, is that we're actually able to get a very good sketch for that graph, as long as it's a line again. Because all you need to graph a line is 2 points. So let's take a look at our sketch here. So here's the grid, and our x-intercept was 1/2. So right about here. So here's the x equals to 1/2. Our y-intercept was at 0, 2. So there we go. These are the 2 points that we're using to make a sketch for the line. There we go. Very simple sketch. Alrighty, so now let's take a look at another problem here. And I like this one a little bit more because we don't have to make a sketch. But also the function is a little more complicated, and excellent opportunity to practice factoring. So let's consider the function f of n is equals to 3n squared minus 12n cubed minus 15n squared. And we want to find out all the zeros for f. So again, this time around, since we're trying to find the zeros, we're trying to see this time around, okay, what n values make the function 0. So in other words, when is f of n equals to 0? So we set our function equals to 0. So we have 3n to the 4th minus 12n cubed minus 15n squared equals to 0. Now this one here might look a little bit daunting, but I think it's not too bad as long as we factor correctly. Alright, so is there a GCF in the 3n to the 4th minus 12n cubed minus 15n squared? I think I do. It looks like the greatest common factor is a 3n squared, because the 3, the 12, and the 15, they can all be divided by a 3. And for the variables, this one's n to the 4th, n cubed, and n squared, so I can take out an n squared from all of them. Now once we factor out the 3n squared, what are we left with? Well, one trick that I like to do is divide by the GCF. Okay, so once we factor out the 3n squared, what are we left with? So what's remaining after we divide by the 3n squared? Well, let's see, we're going to have 3n squared, parentheses, 3n to the 4th divided by 3n squared, the 3's cancel, n to the 4th divided by n squared, looks like we're left with an n squared, minus 12 divided by 3 is 4, so we take a 4n, and 15 divided by 3 is 5, and n squared divided by n squared, and that just cancels. They're just left with a 1 here. This was left with a 2. Okay, so there we go. We factor it out, but we can keep on factoring even further, because I think that we can factor out the n squared minus 4n minus 5. So what are those factors though? Let's see. Alright, so once more, two numbers that multiply to a -5 and add up to a -4, which I think it's the one that we just did, right? Lucky for us. I think the answer was a -5 and a 1. So we should be getting an n minus 5 and an n plus 1. Okay. Now this was equals to 0, so we once more use the zero product property, and I'm just going to make this a little bit smaller here. So we're going to be getting, let's see, 3n squared equals to 0, n minus 5 equals to 0, and n plus 1 equals to 0. So it looks like n is equals to 0 here, because 3 times, if we divide by 3, divide by 3, so 0 divided by 3 is 0. So if we think about it, n squared equals to 0, then that means that n is equals to 0. N is equals to 5 here, and n is equals to -1. So it looks like the zeros are n equals to 0, n equals to 5, and n equals to -1. Okay. Now what about the y-intercepts? Same idea. To find the y-intercepts, then we need to set the n equals to 0. Or in other words, we need to find out, hey, when is, or sorry, what is f of 0? And in this case, if the n is 0, then we're going to be getting, let's see, f of 0, that's just going to be 3 times 0 to the 4th minus 12 times 0 cubed minus 15 times 0, which is just a 0. So f of 0 is equals to 0. So there we go. X